Hello. We are now nearly done with the conceptual details of thermodynamics. I have covered all the key concepts, and you should now be in a position where you can begin to tackle most of the problems you will encounter. There is really only one final issue that we need to touch upon, and that is the business of modelling changes of states. In other words, we need to think about the mathematics we need to describe processes such as the change from solid to liquid or liquid to gas. The key thing to realise when looking at phase transitions is that so far in all the mathematics I have presented, we have exploited the properties of so-called analytic functions. An analytic function is any function f that is locally given by a convergent power series. In other words, a function is analytic if it is possible to write the function using the Taylor series shown below. An important, but not sufficient, requirement for the function to be analytic is that derivatives of the function must all be equal to finite numbers. Obviously, if any of the derivatives of the function are infinite, then you will be adding infinity to this series and it will not converge. It will be equal to infinity. With this in mind, let's consider phase coexistence. Here I have a picture of a glass of water in which I have placed some ice cubes. My question for you is this. If the system is at atmospheric pressure and if the liquid and ice in the glass are in equilibrium, what temperature must this system be at? Hopefully, you were able to work out that this system was at a temperature of 0 degrees C or about 273 Kelvin. In other words, the system is at the melting point. We know this because we know that in order to be at equilibrium, the intensive quantities, in this case the temperature, must be uniform throughout the system. Notice that we have a two-phase system here. The ice is one phase and the water is a second, different phase. Ice ceases to be ice at temperatures higher than the melting point. It becomes liquid water. Similarly, liquid water becomes solid at temperatures lower than the melting point. The system therefore must be at the melting point, as this is the only temperature at which the solid and liquid can coexist, and at which they can be in equilibrium. Now let's consider a second easy question. Here I have a cartoon of a solid, a liquid, and a gas. In each of these pictures I have the same number of atoms, the same amount of stuff. What I would like you to do is to draw a graph of how the volume changes as you increase the temperature over the boiling point. Pause the video and take a moment to do this now. Now hopefully you drew something like the graph shown here. In fact, I hope you drew something considerably better than the graph shown here. Really, the volume of the liquid will expand as the temperature is increased, as will the volume of the gas. This is beside the point, however, as I have drawn a graph of how the volume changes as you move across the coexistence pressure. This will allow me to make my point here more easily, as we will see in a moment. None of this is particularly important though, as what I was really looking for was the discontinuity. That is the step change in the volume of the system that happens as the system moves from liquid to gas. There is a discontinuity at this phase boundary because we have a sharp boundary between the two states of matter. In other words, upon boiling, the system will become a gas, and the system will not be a liquid at temperatures higher than the boiling point. Similarly, at temperatures lower than the boiling point, the system will be liquid. It will not be a gas. Furthermore, we know from school that gases generally take up much more volume than liquid. The step is important because at this point on our curve, the function is not continuous. In other words, at this point, the limit of v of x plus epsilon, as epsilon tends to 0, is not equal to the limit of v of x minus epsilon, as epsilon tends to 0. Here notice that I am using the symbol x to indicate the pressure. To make this point completely transparent, let's consider what these two limits are doing. If we consider the one on the left-hand side of the equation first, we are taking the value of the function x, which I will show using a blue dot here. We then add to this a small number epsilon. I will represent the value of the function at the point x plus epsilon using the green dot. We now reduce epsilon down to 0, and we see that eventually the green dot moves black over the blue dot as shown here. Let's now turn to the limit on the right-hand side of the equation. We now subtract epsilon and thus draw a green dot here. As we reduce epsilon down, we now see that the green dot does not overlay the blue dot as it did before because of the step or discontinuity in the function. We next recall that all thermodynamic variables can be written as a derivative of a thermodynamic potential. The relevant thermodynamic potential here is the enthalpy, H, and remember that dH is given by the expression shown here. In a procedure that is by now hopefully familiar, we can use this result to express the volume of the system as the partial derivative of the enthalpy with respect to the pressure at constant entropy. We thus find that we can rewrite our discontinuity in the volume of the system as a discontinuity in the value of a partial derivative of a thermodynamic potential as shown here. In other words, at the coexistence pressure, the first partial derivative of the enthalpy with respect to pressure is not continuous. With this in mind, I would like you to draw a graph that shows how the enthalpy of the system changes as you move across the coexistence pressure. Pause the video for a moment and take some time to do this diagram. You should have drawn something like this. We know that the derivative of a function at every point is equal to the gradient of a tangent to the curve. Thus, if our function has a discontinuous derivative, this suggests that the gradient will change abruptly at the point where the derivative is not continuous. In other words, our curve will have an abrupt dogleg at the coexistence value because the volume of the liquid and gas are not equal, and because the volume is equal to the partial derivative of the enthalpy with respect to the pressure. This neatly brings us back to analytic functions, which I told you were functions that could not be expanded as a Taylor series. Obviously, if there is a phase transition, the enthalpy is not analytic, because as we have seen, at phase boundaries, the partial derivatives will be discontinuous. This implies that higher derivatives will be infinite and that the Taylor series will thus not converge. Let's be totally clear. The Taylor series expansion of a thermodynamic potential will converge locally for most values of the thermodynamic potential. This is the basis of most of the results that we have derived in all the other videos I have presented on classical thermodynamics. The bog standard real analysis that is the workhorse of classical thermodynamics only really works when our function is expandable as a Taylor series. If we have discontinuities, we have to use other tools when we want to integrate things. If we don't go anywhere near phase boundaries though, all the maths that I've introduced thus far works fine. Furthermore, if we don't dwell too much on phase boundaries in this course and the mathematics that we use to describe them. What is important to know, however, is that phase boundaries occur whenever we have discontinuities in the derivatives of our thermodynamic potentials. Furthermore, we classify phase boundaries based on the derivative that is discontinuous. So if the first derivative is discontinuous, we state that we have a first-order phase transition. If any other derivatives are discontinuous, we state that the phase transition is continuous. Thank you for your attention.